Robbins. This is my second time at Western. I graduated earlier with a graphic design degree and a marketing minor, and now I am back for my data analytics certificate. I am going to talk very fast during this video because I'm struggling to keep it less than 20 minutes, so here we go. First thing we're going to look at is body data. I have library RPart, library Carrot. I would run these, but I have been in here a lot today, and I could tell from my packages that here is Carrot, here is RPart. These are already installed, so I'm not going to rerun them, but I do have them in my code. Where's RPart? There it is. Okay, so not going to run these because they're already down here, but I could. First thing we need to do is bring in some data. We are going to grab this body measurements data. All right, it brings it in kind of an Excel format. That's not what we're going to look at. We care about that it's over here. 252 observations, that's rows, 15 variables. That's the different columns. If I click down, I can see them all here. First thing we want to do before we build our model is separate our data or partition our data out so that we have some for training, some for testing, so that the model is not basing everything on all the data in here. So I'm going to do a 70-30 split. Training data, this will show up over here. Testing data, this will show up over here. Body measurements is where we're pulling this from. This is a 70-30 split. 1 through 176, that's rows. That's 70% of the rows. Comma says take all of the variables or columns. Body measurements again down here. 30% of the data is rows 177 through 252. Columns says give us all of the columns. Comma says give us all of the columns or variables. So I'm going to run these two. They're going to pop up over here. And there we have them. Now we're going to build our model. We're doing a regression tree. The regression tree is because we are solving for a numerical value here. It's not a yes or no thing. So I'm calling it a regression tree model. That's what will show up over here. Our part is a function of the library that we ran up here. Body fat is what we are trying to solve for. This is our formula. Carrot is the divider in the middle of what we're solving for, and then our other variables. The period is every other variable, or if I click down on this, all of these columns. We want to use all the columns except for body fat to predict body fat. Data is the training data. That's the data that we used here when we split it because we want it to have separate data for testing later. Method is ANOVA because we're doing a regression tree here. So when I run this regression tree will pop up over here, and there we have our regression tree. All right, now we're going to do our testing. I'm calling it regress predictions. That's what will show up over here in our environment window. Predict is a function of the libraries that we ran earlier. Regress tree model is what we used up here, the training data, to build our model with. We are saying with this, hey, we want to take this training data model and use that on this testing data that you haven't seen before, to make these predictions to test the model. Type is vector because we're doing ANOVA here for a regression tree. So I'm going to run this, and here we have our regression predictions. Now we have to figure out how accurate it was. We're going to do that using RMSE. That's the root mean squared error. This is what I'm calling it. This is what will show up over here. We're going to do that by taking our predictions, what we did here, and we're going to compare that to the actual data and see how far apart they are. Then we're going to square it. Then we're going to take the mean or average of that. Then we're going to take the square root of that. That's how we're going to figure out how accurate this model was. I'm going to hit run. That's going to pop up over here. And our regress RMSE, 2.23 roughly. For RMSE, lower the value, closer to 0, the better. 2.23 for this is pretty good because when I look at that data in the Excel sheet, body measurements I think ran between 0 and 47.5 is roughly 2.23. That big a span when you're looking at that much data. No, if our data went from 0 to 10 or 0 to 5, this would not be quite so accurate, but this is what we're going to use to compare when we do our other model. So the other model we're doing for this is a linear regression model. That's what I'm going to call it. That's what's going to show up over here. This is a function of the libraries that we installed earlier for linear model. We are still predicting for body fat, and we are still going to use all of the other columns or data in there to predict for this. The data we're using is training data. The reason we can put this in here is because we already did training data for this. If we had not run this regression tree model and partitioned our data up here already, we would have to do this again, or it would not know what we want to pull from training data. But that's over here. We have it to pull from, so when we run this, our linreg model is going to show up over here. Run it. Here it is. All right, next we got to make our predictions or train the model. I'm calling that linreg predictions. That'll show up over here. Predict is a function of the libraries that we ran earlier. Linreg model and testing data. This says we're going to take what we did here the model that we built with our training data, and we were going to use the new data, the testing data, the data that it's never seen before, to use that model to make the predictions on that data. So we're going to run that, and that shows up over here. Or so, no, sorry, no, that shows up over here as our LinReg predictions and down here in our console window. Now we have to get a measure of how good those predictions were, so we're going to do root mean square error again. This time I want to call it this so that it shows up differently over here to compare to this. We're doing the exact same formula, but we have these inputs here instead of these. So we are taking our predictions from this model and seeing how far those were from the actual data here. We're squaring those, then we're taking the average of that, then the square root of that, and when I run that, it'll show up over here. So here it is. This is from the linear regression model, 0.93. So this is closer to 0 than this. So for this particular example, when we're solving for predicting body fat, the linear regression model is the one that we would want to use for that. So moving on, because we've got to look at some loan data now. Let's clear this out because we don't want to see any of this for our second example. All right, scroll to the top of our code. I have these in here again. Again, I can see that they're installed over here. Not going to run them again, but we do need data, so let's pull that in. This time we are looking at loan applications. Open that up, bring it in. Okay, brings it in just like the Excel. We can look through this, but I'm going to go back to my R code for, let's close that out. Going to go back to my R code for the loan data. When I look at this, I can see 272 rows, 12 variables. Here they all are. This is problematic. We don't want characters in here. We would prefer for these to be numerical or factors. To kind of get a better handle on this, I can plot the data as a scatter plot. When I run this, we get an error because this window is not big enough. So let's just bring this up a little bigger. Let's run that code again. And now, there they are. Okay, I can zoom in. Will it show you this? Will it not? I think it will. It's in my recording. I can look at this and tell gender. There's only 2 outcomes here, so probably male or female. Married, 2 outcomes, probably married or not married. I can go on and look at some of the other ones to just kind of confirm, yeah, these need to be converted to vectors. And the code to do that, we're going to say, hey, look at loan applications. Take this column of gender, and we want that to be a factor, not a character. And this, we're also telling it we would like for this title to stay the same. We still want it to be called gender. So when I run this, this is going to change from a character to a factor. And it did. So we need to do the same thing for married. We need to do the same thing for dependents. So this is all the same code, just with these different column headers in here. Same thing for education. So let's bring this down so we can look at all of these things. Okay. Self-employed should change. Now we're going to look at property area. And did it get, yes, loan result, good. Okay, there's one more thing that still gives me pause over here, and that's the credit history. This is ones and zeros. I can look in my scatter plot and see that. I can also look in the Excel and see that. I would prefer that this be factored as well so that it doesn't throw off any of our calculations. It's the same code up here to do that as we did for these, but this is, it's going to change this from a number, whereas it was changing these from characters. So let's run this. Okay, data looks good. We can close this up for just a moment. First method we are going to do is a logistic regression model. Before I build that, I want to run, I'm going to call this my control. I'm running train control from the libraries that we installed earlier or ran earlier. That's going to put my control over here. That's just what we're calling it. The method here is cross-validation. That's CV. The number is 7. That's 7 k-folds. We could use 5. We could use 10. I'm choosing to use 7. When we do this, we are telling the model, hey, I would like you to partition the data into 7 parts for testing, 1 part, or 7 parts, 6 parts, 6 parts for training, 1 part for testing, and run it 7 times. That's going to become important later on down here. The set seed, oh, I'm going to go ahead and run this so that my control pops up over here. All right, my control, good to go. Set seed. When I run this, it's not going to show up over here. It's only going to show up down here. When we do a set seed, we are doing this so that we can reproduce our data. It could be 100. It could be another value. We'll do it with a different one in a minute. But for now, we're going to run it as 100. Good. All right, now this we are going to use to build our model and test our model. I'm calling this logistic log reg model, because it's a logistic regression model, this is what's going to pop up over here. Train is a function of that library. Lone result is what we're trying to solve for. This is our formula. This is the tilde to separate the variables. The period says use all of the columns or the other variables to predict for this. Data is lone applications. We can use this instead of the test and train because we are going to use this down here to separate out for training and testing. That's why it's okay to use the full data set here. Method is GLM. That's just because we're doing a logistic regression model. Family is binomial because we're solving for yes, no. We want to know, is this person likely to qualify for a loan, yes or no? Train, and I didn't say this in the data, but I think probably what this credit history is either yes, they have credit history, no, they don't, or yes, their credit history is considered good by the bank, or no, it's considered bad. So, but this is too much to look at. So that's what we're solving for. The result is going to be a yes or a no. TR control is going to be my control. That's what we did when we ran this code and put this over here. Again, that's telling it divide it into sets of 6 parts for training, 1 part for testing, run it 7 times. So when we do this, we're going to make the model, we're going to test the model, and now we have that over here. All right, that really doesn't tell us anything about accuracy though, or how good this model is. So I'm gonna do this just so that it brings us up some results to look at. And when we do that, we see it was, this is our cross validation, 7-fold, good. Accuracy is 0.04. Now this is a little different than RMSE because this we want a higher value. This is actually a percentage, so it would be about 84%. We would like to be close to 100%. That's gonna be our value for accuracy with this logistic regression model. Moving on to the classification tree. That's the other way we're going to do it. We've got to do training data and testing data for the classification tree so that it knows to hold out some values. This is a 70-30 split. 1 through 90 are the rows for 70% for training. Comma says take all the columns. Testing data 30%, 191 through 272 for our rows. Comma says all the columns. So these are going to pop up over here when we run these 2 lines. There they are. Now we are going to build our model. It's a classification tree because we are looking for a yes-no answer. A regression tree would be if we were looking for a numerical value. Our part is a function of that library. Lone result is what we are solving for. Tilde separates the formula here. Period says run all those other variables or columns to look for this result. Data is training data, which we did up here. So we don't want to pull from all of the loan applications. We're going to hold some back. Method is class because it's a classification tree. When we run this, our classification tree is going to pop up over here. Let's run it. There it is. This is how we make our predictions or test the model. This is what we're going to call it, class predict. This is what will show up in our environment window when we run this. Prediction is a function of the library. Class tree is what we did here. This is our model. Now we are telling it, use this model where we use the training data to run our predictions or testing on the data that you haven't seen before, the testing data, this data here. Type is class because it's a classification tree. Let's run it. There it is. This is how we're going to get our accuracy. First, we want to make a table. This is going to put the table over here. So when we run this, the table is going to be a confusion matrix of class predictions. So what we predicted here versus what the actual values were. So we're going to run that. It'll pop up over here. And there it is. I want to see it as a confusion matrix down here, just visually. This doesn't really, I mean, you can get your information from here, but I think it's easier to look at down here. So I'm going to run class matrix to see that down here in my console, run it, there it is. Okay, so this is, it predicted no, it was actually no, predicted yes, it was actually a yes. This is important because we need these for this formula that's going to determine our accuracy. This is what accuracy is going to look like, class accuracy over here. This is a formula from the libraries that we ran. What we're doing is we're taking all the times that it got it right, so the 11 and the 47, and then we're dividing that by all of the predictions that were made in here in the matrix, and that's going to give us our accuracy. So I'm going to run that and it should show us our accuracy. Yes, here's our accuracy over here. This is about 71%. This is just to get it to show up down here. I did that because I didn't actually send this over here to compare our accuracy to. So when we do this, it's just going to give us this same accuracy here down here. But I'll run it. I put it in there, so I'm going to run it. All right, 0.07. So here we have 0.07 for the classification tree. We have 0.84 for, or 84%. Sorry, 84% accuracy for the logistic regression. We have only 70% for the classification tree. So what we want to go with here is the logistic regression. And I actually should probably change this and try it with a different value here, just to, let's run this again and make sure that we're still getting a pretty good, yeah, so that accuracy there is still pretty close, 84%, it's still very close. And we could run this a couple more times, but I'm going to say based on this that what we want to go with this is the logistic regression model. So that is my capstone project for BDAN 310, summer of 2026. I really hope this version is less than 15 minutes.